After studying this module, you shall be able to know what is surface tension and surface energy, know how do we measure surface tension, study the applications of surface tension. First, we shall see the adsorption from solution. In the earlier modules, we have seen the adsorption of gases on the surface of a solid adsorbent in detail. Now, we shall discuss the second category of adsorption process, which is clearly understood. This is the adsorption of dissolved substances from the solution. Before we discuss this, we shall understand the phenomena of surface tension and surface energy as they are related to adsorption. Looking at what is surface tension and surface energy. If we consider a close packed arrangement of spherical molecules in a solid, we know that each molecule in the bulk is bounded by 12 other molecules. Therefore, the bond strength is E by 12, where E is the binding energy or the cohesive energy per molecule equals to capital E by Na, where capital E stands for the cohesive energy per mole. However, if we consider a molecule on the surface layer, then each such molecule is bounded only by 9 neighbors. Therefore, the total binding energy of the surface molecule is 9E by 12, which is equals to 3 by 4E. Thus, we see that the surface molecule is bounded with only 75% of the binding energy as compared to a molecule in the bulk. In other words, we can say that the surface molecule has higher energy relative to a molecule in the bulk. The same picture is true in the case of liquids. The molecules in the bulk of the liquid are surrounded by other molecules from all its size, such as the net force of attraction is 0. However, the molecule at the surface is surrounded by more number of molecules inside the liquid as compared to that in the vapor phase. It is well known that the attractive forces tend to decrease the energy of the system, and in the present case, the attractive forces are more predominant in the bulk of the liquid than at the surface. Thus, we see that the surface molecules are associated with higher energy as compared to those in the bulk of the liquid. It is because of this extra energy of the surface molecules as that they experience a net inward pull and move into the bulk of the liquid, that is, from a state of high energy to a state of low energy. Consequently, number of molecules at the surface become less as compared to that in the bulk. As a result of this, the distance between any two surface molecules becomes greater than that in the bulk. In order to acquire a normal distance between them as before, the surface molecules tend to move closer to one another. That is, the surface of the liquid tends to contract as if it were under some sort of tension. This force that tends to contract the surface area of a liquid is called as surface tension. Mathematically, it is defined as the force acting per unit length at right angles to any line drawn on the surface of the liquid. It is represented by gamma. Figure shows A, the surface tension phenomena, and B, a stretched film on a frame. If we wish to increase the area of the surface, then we need to bring some molecules from the bulk of the liquid to its surface. This process requires energy, and therefore some work will be done in bringing the molecules from the bulk to the surface against the inward attractive pull. The amount of work done in increasing the surface area by unity is called as surface energy. This surface energy acts as a measure of the inward pull. As larger the attractive forces, more will be the amount of work done. Mathematically, this can be explained as, let us consider a liquid film stretched on a movable frame of length L as shown in figure, and we wish to increase the surface area of the film by an amount dA. The work done in the process will be F into dx, where F is the force required to move the wire by a distance x. During this process, the Gibbs energy of the film increases by gamma dA, where gamma is the surface Gibbs energy per unit area. Equating the two, we get F dx equals to gamma dA as our equation 1. But dA is equals to twice into L dx. The factor 2 appears as the film has two sides. This is our equation 2. Substituting equation 2 in equation 1, we get f dx equals to gamma into 2L dx, or f is equals to gamma into 2L as our equation 3. The total length of the film in contact with wire is 2L. Thus, the force acting per unit length, that is surface tension, gamma is equals to F by 2L. This force of surface tension opposes the increase in surface area. The SI unit of surface tension, gamma, is newtons per meter, which is equal to Gibbs energy per unit area in joules per meter square. Thus, surface tension is numerically equals to surface energy. We have surface tension equals to force by length, which is equals to Newton per meter in SI units or dynes per centimeter in CGS units. And surface energy is work done by area, which is equals to force into distance divided by distance square, which again comes out to be newtons per meter in SI units or dynes per centimeter in CGS units. Both have the dimensions same as mt to the power minus 2. Now we shall see the measurement of surface tension. If we can measure the force required to stretch the film on a movable frame, we can measure the surface tension. There are a number of devices made for the purpose for measuring the surface tension. A device called Denoy tensiometer or ring pull device is one such convenient and simplest device used. It is shown in figure. The device is calibrated by the addition of small masses to the end of the beam and setting up of the torsional scale to keep the beam in level. For measuring the surface tension, the ring is placed on the beam and the level of the liquid, whose surface tension is to be measured, is raised until the ring is completely immersed in it and the beam is level. Now, the height of the platform on which liquid is kept is lowered and the ring is pulled out slowly by turning the torsion wire. Throughout the experiment, the beam is level. When the ring just pulls free from the liquid, the torsion scale is read. The reading can be converted into an equivalent force F with the help of calibration. This force can be obtained by multiplying the length of the wire that is in contact with the ring and the surface tension gamma. The former is 2 times the circumference as the liquid is in contact with both the inside and outside of the ring. An empirical correction factor F is also introduced into the expression. This accounts for the shape of the liquid being pulled up and the fact that the diameter of the wire itself, 2r, is not 0. Thus, we have the expression 4 as F equals to 4 pi r into gamma into F. The values of F as a function of r and small r can be obtained from the literature. Making use of the equation 4, we can find the surface tension of the liquid. Another method similar to the ring pull method is the Wilhelmy slide method. Figure shows the Wilhelmy slide apparatus. An extremely thin plate such as a microscope cover glass or a mica sheet is hung from one arm of the balance and is allowed to dip in the solution. This is shown in figure. The downward force acting on the slide due to surface tension is gamma into P, where P is the perimeter of the slide. If F and Fa are the forces acting downward when the slide is touching the surface and when it is suspended freely in air respectively, then we have F equals to Fa plus gamma P as our equation 5. This equation 5 is based on the assumption that the depth of the immersion is negligible. It can be used to measure equilibrium surface or interfacial tension at an air-liquid or liquid-liquid interface. Another device commonly used in laboratories to measure surface tension of the liquids is stalagmometer. That is shown in figure. It consists of a small glass bulb. This is attached to a fine capillary with a sharp edge from which the liquid falls drop by drop. The method is based on the assumption that the force of surface tension acts around the circumference of the capillary and holds the two parts of the liquid column together. This force acts in the upward direction and is balanced by the force due to the weight of the liquid acting in the downward direction. As the size of the liquid drop increases, its weight increases. When the latter becomes infinitesimally greater than the upward force of surface tension, the drop breaks off from the apparatus and falls down. Care must be taken that the drop size and the drop rate should be small so that the drop falls off under its own weight only. If r is the radius of the capillary tube and m is the mass of the liquid drop, then we have at equilibrium upward force is equals to downward force, or 2 pi r times gamma is equals to mg, as shown in equation 6, where g is the acceleration due to gravity. To avoid the measurement of r, one makes use of the relative method, that is, the experiment is repeated with a liquid, say water, whose surface tension is known at that temperature. Thus, we have m1g equals to 2 pi r gamma 1 and mwg equals to 2 pi r gamma w, or gamma 1 is equals to m1 times gamma w divided by mw. In the drop weight method, mass of n drops of liquid or water are calculated, and from this the mass of a single drop of liquid or water can be calculated. In the drop number method, the number of drops in a definite amount of liquid volume, say V, is counted. The mass of a single drop of a liquid is then counted from the density measurements as follows. M1 is equals to V1 into rho 1, which is equals to capital V by N1 times rho 1, as at equation 8, where M1 and V1 are the mass and volume of single drop of the liquid respectively. N1 is the number of the drops and capital V is the total volume of the liquid. If we take the reference liquid as water, then we have equation 9 as gamma 1 by gamma w is equals to m1 by mw, which is equal to rho 1 into nw divided by rho w into n1. Now we shall study the applications of surface tension. Surface tension is an important phenomena that has many applications. Some of them are discussed as follows. Number 1 is the shape of the liquid drops. We have studied that the surface tension reduces the surface area of a liquid. Since for a given volume, sphere has the least surface area, the drops of a liquid are spherical in nature in the absence of gravity. Number 2 is the capillary action. Have we ever wondered how does underground water rise onto the surface of earth or inside the plants, or how oil rises in a wick? These all familiar examples are of capillary action. When a capillary tube is partly immersed in a liquid, there occurs either a rise or a fall of the liquid level inside the tube. In other words, the liquid is present at different levels inside and outside the capillary tube. The nature of the liquid vapor interface being different, flat outside and curved inside the tube. This phenomena of rise and fall of a liquid in a capillary tube is called capillary action. It occurs due to surface tension of the liquid. The two cases are discussed in detail as follows. If the adhesive forces, that is the attractive forces between unlike molecules, that is the liquid molecules and the solid surface of the capillary tube, are greater than the cohesive forces, which are the attractive forces between the like molecules, that is between the liquid molecules, then the liquid has a tendency to spread on the solid surface of the capillary tube. These type of liquids are called wetting liquids. They rise in the capillary tube with their meniscus facing concave upwards. The angle of contact is less than 90 degrees. The latter is defined as the angle measured within the liquid between the wall of the capillary tube and the tangent drawn at the liquid surface of the tube. This is depicted in figure, which shows the measurement of contact angle. On the other hand, if the cohesive forces are greater than the adhesive forces, then the liquid has a tendency to detach from the solid surface of the capillary tube. These type of liquids are called as non-wetting liquids. Their level falls inside the capillary tube with their meniscus facing convex upwards. The angle of contact for these liquids is greater than 90 degrees. This has been shown in figure. Mathematical expression is as follows. We know that the surface tension is responsible for capillary action. We shall derive a mathematical relation between the liquid level in the capillary tube, surface tension and the density of the liquid. Let us suppose we have a wetting liquid of density ρ that rises to height h in a capillary tube of radius r. The force of surface tension will act around the circumference of the capillary tube in the upward direction, and will be responsible for the rise of the liquid level in the capillary tube. This is shown in figure as the rise of a wetting liquid inside a capillary tube. From figures we see that the force acting in the upward direction is gamma cos theta times 2 pi r. This is balanced by the force due to weight of the liquid acting in the downward direction equals to mg equals to pi r square h. At equilibrium, we have our equation 10 as gamma cos theta times 2 pi r equals to pi r square h, which gives gamma equals to 1 by 2 into h rho g r divided by cos theta as our equation 12. The height h can be measured using a cathetometer and radius of the capillary tube r using a travelling microscope. Thus, making use of equation 12, we can evaluate the surface tension gamma of the liquid. The value of theta for most of the wetting liquids is very small, that is close to 0, so that cos theta becomes 1 and we have gamma equals to half h rho g r as our equation 13. For non-wetting liquids, the value of h will come out to be negative. For example, in the case of mercury, the value of theta is 180 degrees and cos 180 is -1, making h negative. This is the reason when a mercury drop falls on a clean, level surface, it becomes a truncated sphere. Talking of the pressure difference across the curved surface, we have the Young-Laplace equation. Thomas Young and Pierre Simon de Laplace proved that there exists a pressure difference between two sides of the curved surface. They formulated an equation known as Young-Laplace equation, given by equation 14 as P alpha minus P beta is equals to 2 gamma by r, where P alpha and P beta are the respective internal and external pressures and r is the radius of the spherical surface. The equation is based on the fact that some work is always required for an infinitesimal increase in the surface area of an interface at constant temperature and constant volume of the system. It can be derived as follows. Let us consider a single spherical drop of liquid alpha phase in equilibrium with its vapor, which is the beta phase. At a constant temperature T, let P alpha be the internal pressure of the drop and P beta be the external pressure of the vapor. Let this liquid drop be cut into two halves by an imaginary plane to get two hemispheres as shown in figure. Figure shows a liquid drop cut into two hemispheres by an imaginary plane. P alpha and P beta are the internal pressures of the drop and external pressure of the vapor respectively. The force of surface tension tends to reduce the surface area and hence volume of the drop and acts along the circumference of the hemisphere. The former will then be equals to 2 pi r gamma, where gamma is the surface tension of the liquid. The force of surface tension is opposed by the pressure difference across the liquid-vapor interface, which tries to increase the surface area and hence the volume of the drop. The force acting due to the pressure difference is equal to the pressure difference multiplied by the projected area of the hemisphere, that is P alpha minus P beta times pi r square. At equilibrium, the two opposing forces will balance each other, and we have equation 15 as P alpha minus P beta into pi r square equals to 2 pi r gamma. Equation 15 on solving gives the Young-Laplace equation 16 as P alpha minus P beta equals to 2 gamma by r. There is another method to derive the Young-Laplace equation. Let us consider a syringe fitted with a piston and a sharp needle in thermal equilibrium with the surroundings at any temperature T. It is filled with an incompressible liquid of the surface tension gamma. In order to form a liquid drop, some pressure P alpha greater than the external pressure P beta has to be applied on the piston of the syringe. The net work done in the process will be equals to dW equals to P alpha minus P beta times dV, where dV is the volume change as shown in equation 17. This net work done increases the surface area of the liquid drop. Therefore, we can also write dW is equals to gamma ds, where ds is the increase in the surface area as shown in equation 18. Equating the above 17 and 18 equations, we get P alpha minus P beta into dV equals to gamma ds as our equation 19. If the radius of the liquid drop increases by a small amount dr, then dV equals to 4 by 3 pi r plus dr cube minus 4 by 3 pi r cube equals to 4 pi r square dr, and ds is given by 4 pi r plus dr square minus 4 pi r square equals to 8 pi r dr. Substituting the values of dv and ds in equation 19, we get equation as p alpha minus p beta into 4 pi r square dr equals to gamma times 8 pi r dr. On solving this, we get equation 20 as p alpha minus p beta equals to 2 gamma by r. From the Young Laplace equation derived above, we see that the pressure inside a spherical drop is always greater than the pressure outside by an amount proportional to the surface tension and inversely proportional to the radius of the drop. When the surface becomes flat, the radius of curvature becomes infinite and the pressure difference reduces to 0. The equation breaks down before the radius tends to 0, thus avoiding pressure difference tending to infinity. If the interface is not spherical but has R1 and R2 as the maximum and minimum radii of curvature at any point, then we have equation 21 as p alpha minus p beta equals to gamma into 1 by R1 plus 1 by R2. The Young Laplace equation derived above has been experimentally validated by the phenomena of capillary action. We know that the liquid is present at different levels inside and outside the capillary tube. Since the liquid-vapor interface is curved inside but flat outside, a relation between the rise in the liquid level inside the capillary tube h, radius of the capillary tube r, surface tension of the liquid gamma, and the relative densities of liquid and vapor phases rho alpha, rho beta is rho alpha minus rho beta times gh equals to 2 gamma cos theta by r as our equation 22. Here, theta is the contact angle. This equation bears the same results as the equation. Now, we shall see the formation of bubbles. The formation of bubbles is basically due to surface tension. From the Young Laplace equation derived above, we have seen that the pressure acting on the concave side of the drop is greater relative to the one acting on the convex side. This gives rise to the formation of stable bubbles. With increase in the pressure, the chemical potential of the liquid also increases by an amount d mu L equals to Vml into dPl, where Vml is the molar volume of the liquid. Since the liquid is in equilibrium with vapor, the chemical potential of the vapor also increases by the same amount, that is d mu L equals to d mu G as our equation 23. But we have d mu equals to minus Sm dt plus Vm dP. At constant temperature T, d mu is equals to Vm dP as our equation 24. Using equation 23 and 24, we get Vmg dP equals to Vml dPl as our equation 25, where P is the vapor pressure of the vapor. If the vapor is assumed to be ideal and integrating equation 25, we get integral P1 to P RT by P dP equals to integral P1 to P2 Vml dPl. If Vml is assumed to be constant, then the above equation can be written as RT ln P by P1 equals to Vml P2 minus P1 as our equation 26. Using the Young Laplace equation 16 in the above equation 26, we get RT ln P by P1 equals to Vml into 2 gamma by R as our equation 27. If the interface between the liquid and the vapor is planar, that is R is tending towards infinity, then P equals to P1 equals to P0 as the saturation pressure. Thus, we can write equation 27 as ln P by P0 equals to Vml by RT into 2 gamma by R equals to m by rho RT into 2 gamma by R, where m and rho are the molar mass and density of the liquid respectively. Equation 28 is known as the Kelvin equation for liquid droplets. The Kelvin equation can easily explain the processes like vapor condensing in small capillaries at pressure much below the saturation pressure. If the liquid wets the capillary, R is negative and meniscus is concave upwards. It also explains the phenomena of supersaturation, extensively useful in the preparation of compounds and cloud seeding, and the mechanism of emulsion breakdown, that is the Oswald ripening. Now we shall summarize what we have learnt in this module. The force that tends to contract the surface area of the liquid is called as surface tension. It is numerically and dimensionally equal to surface energy. Surface tension can be measured by different devices such as denier, tensiometer, Wilhelmy slide apparatus and stalagmometer. Surface tension explains the spherical nature of liquid drops, capillary action and the formation of stable bubbles.